प्यारे बच्चों, today we will discuss time response specifications. So several time response specifications are delay time, rise time, percent overshoot, peak time, settling time, and finally expression of output. So these are five specifications which specify any system. So here expressions are given. You can calculate delay time, rise time and other parameters by calculating these two parameters, zeta and omega n. Omega n is the natural frequency. This is the damping factor. So first one is the delay time, Td, which is equal to 1 plus 0.7 zeta upon omega. So this is the delay time. Rise time is given by pi minus alpha upon omega d, where alpha and omega d can be calculated by these two expressions. Alpha is the phase angle, that is tan inverse under root 1 minus zeta square upon zeta, and damping frequency, which is given by omega n under root 1 minus zeta. So to calculate rise time, we have to calculate these two parameters. First, phase angle by this expression, and second, damping frequency by this second expression. Then we can calculate rise time by using pi minus alpha upon omega. And to calculate delay time, we have only zeta and omega n, which can be obtained from general second order system. So what is the general transfer function for second order system? This is omega n square upon s square plus twice zeta omega n s plus omega n square. So any system which is defined in terms of this is general expression, then we can compare given system by this standard expression, and we can calculate natural frequency and damping factor, and from there we can start other calculations for time response specifications. So two parameters are required. First one is the zeta, another is the omega. Then from these two values we can calculate all other values. So only two parameters are required. First one is omega n and that is the damping factor. So similarly here we have one more parameter here, peak time. This is the first peak. This is the time to achieve peak value of the output. So Tp is pi upon omega d. And next is the percent overshoot. You can calculate percent overshoot by using this expression, e to the power minus zeta y upon under root 1 over zeta square into 100. And settling time, we have two settling times. We define two different settling times here. First one is 2% settling time, second one is the 5% settling time. So for 2% settling time, ES is 4 upon beta omega and this is 3 upon beta omega. So finally, we have expression for output. We can also use this expression to calculate the expression for output for underdamped system. This is important. Underdamped system means you have value of zeta is in between 0 and 1. This damping factor. So this is the general case for underdamped system. So we can calculate all time domain specifications by using all these expressions. So we have to simply calculate two values first: natural frequency omega n and damping factor zeta. From these two values, we can calculate all other values. So now we will take numerical problems on these expressions. We will solve all specifications for second order system by using all these expressions. So first one is, here we are taking problems. So first one is suppose transfer function, which is the ratio of output to input, is given. That is 81 upon s square 6s plus 81. Find all these values: omega n, zeta, omega d, peak time, percent or so. Okay. So what is the method? So to calculate all these values, first we compare. So compare given expression with standard second order expression. So what is second order expression? So second order expression is omega n is upon s square plus twice zeta omega n s plus omega n. So from here you can get omega n square equals 81 and twice zeta omega n, this parameter. This is 6. So this is the 6. So from here omega n equals 9 and you can calculate zeta from this. 6 upon twice, this is 6 upon 2 times of omega n, that is 6 upon 2 into 9. So you have 6 upon 18, that is 1 by 3. You can also write this is the 0.33 approx. So we have calculated these two values, omega n and zeta. Then we can calculate all these three parameters. What is omega d? Omega d, omega n under root 1 minus zeta square. Okay. Similarly, peak time, you can use this expression pi upon omega t and percent towards root expression. Okay. Which is e to the power minus zeta pi upon under root 1 minus zeta square into 100. So you can use all these expressions, you will get as. So main objective is first find these two parameters. Then we can calculate all other parameters by using expressions. So we can take few more problems. So this was the first problem. One second problem is, suppose transfer function is like this. So this is the given transfer function. And what is standard function? Standard is C by R omega n square upon so here there is the one difference. These two values are different. These two values are not same. But in standard form, these two values are same. Omega n. So now we can write this like 20 upon 25 in bracket 25 upon this. So from here, now you can compare this value. So this is the transfer function multiplied by a constant. This is a constant. So you can compare and get omega n square for given system is 25. And next parameter, which is the coefficient of this, is 7. Okay. So we can calculate easily these two values from here, omega n. So omega n for this is 5 radian per second, and this is the damping factor approximately 0.7. So you can calculate other way. So this is different. If these two coefficients are different, this is considered as omega n square. Term in the numerator is considered as omega n square because you can consider it as a constant 20 upon 25 and you can multiply here in numerator by this factor. So you can calculate this. So this is one type. Now we are checking another example. Suppose GS is given. GS is given for a negative unity feedback system. This is for negative unity feedback. Okay. Determine nature of response. And rise time, peak time, peak overshoot, settling. So what is the method? So first calculate this value Cs by R, that is closed loop transfer function, which is obviously given by 1 plus GSHS. Okay. So for this you can write this is 4 upon S plus 1 4 divided by 1 plus this. So you can solve this. This is 4 upon S square plus S plus 4. Okay. So you can compare this. Comparing we will have this is 4 and twice zeta omega n equal 1. So from here natural frequency is 2 and value of damping factor is 1 upon twice omega n, that is 2. So 1 upon 4, that is 0.25. So what is nature of response? So this value theta will decide value of theta, nature of response. So nature of response is overdamp. Okay. Since value of theta is less than 1. So this is the nature of response, and we can calculate all these values by simply using expressions: rise time, peak time, overshoot, and settling. You can use expressions. Just I am writing answer. You can use this rise time pi minus alpha upon omega t. So you have to calculate two values. First one is alpha, which is obtained from tan inverse under root 1 minus beta square upon theta, and another parameter is damping frequency. So damping frequency, this is obtained by Moman under root 1. So you can calculate these two values. You can check. I think this is 1.318 approximately, and omega is d is 1.936. So from here you can calculate rise time, which comes out to be approximately 9419 seconds. Similarly, by using this, you can calculate 1.623 settling time. So we are calculating here 2%. So this is 2% settling time, which comes out to be approximately 8 seconds. Similarly, when you can also calculate settling time for 5%, that is 3 upon beta omega n. This comes out to be 6 seconds. So these parameters can be calculated by using expressions of rise time, peak time, and settling times. So one last problem here for today. Question is, open loop transfer function is given. So in problem, GS is given. This is given. A. This is given. That is open loop transfer function. And question is, statement of problem is first part. By what factor should the gain K be multiplied to increase the damping ratio from 0.15 to 0.60. This is the first part. Okay. Look here solution for this. what factor should the gain K be multiplied to increase the damping ratio? Okay. So first you have to calculate closed loop transfer function, which is given by Gs upon 1 plus Gs, and from here you can calculate. I am writing directly. This is from here. Cs upon Rs is K upon T whole divided by 2 upon G S plus K. You can solve and check. And comparing with standard form, after comparing with standard form means this is omega n square upon s square plus twice zeta omega n s plus omega n square. So this is the standard form. From here you can find omega n, which is under root k by t, and this factor 2 by t is the coefficient of s, that is twice zeta omega n. This is 2 upon t. Sorry, here omega n is this. This is the omega n square. So you can write this is under root k. Because if these two values are different, then we will take this as omega n square. Okay. So omega n equals under root k, and twice zeta omega n equals 2 upon t. From here you can calculate zeta. No. I think this is also k by t. Check. And zeta equals from here 1 upon under root k. So these two values, omega n and zeta, these two values are important. From here we can find out related value. Suppose we have two values of k1, k2, t1, t2. Okay, for different values of zeta, and suppose zeta is changing from zeta 1 to zeta 2, then these two parameters are changed. Then we can write zeta 2 upon zeta 1 from here. So what factor should the gain k be multiplied? Suppose for this is constant. This is constant. Then there is a variation only in k. Then we can calculate. This is zeta 2 equals 1 upon under root k2 into t, and zeta 1 equals 1 upon under root k1t. Only k is changing in this case. T is constant. Then this is under root k1 upon k2. Okay. So what is the value of this k1 upon k2? You can find out this k1 upon k2 as zeta 2 square upon zeta 1 square, and you can calculate this. So this is, I think, you can put these two values from 0.15 to 0.60. Zeta is changing from 0.15 to 0.60. And zeta 1 is 0.15, zeta 2 is 0.60. So from here you can calculate ratio. Similarly, determine in second part, one more part is here, determine value of t. Second part of this question is determine the factor by which the time constant t should be multiplied to reduce the damping ratio from 0.8 to 0.4. So procedure is same. In this time you have to time constant t is changing. We have t1 is changing from t1 to t2. Suppose zeta is changing from beta 1 to beta 2, and k is constant. This is constant. This time this parameter is constant. Only t is changing with change in damping factor. So you can calculate by same expression. So beta 2 upon beta 1 is 1 upon under root kt2. Here k is constant, kt, and you can calculate. Obviously this is under root t1 upon t2. So you can solve and get zeta 2 upon zeta 1 is given. Zeta 2 upon zeta 1 equals 0.4, 0.8. Okay. So this is 0.5. So under root t1 upon t2 is 0.5. So you can get t2 upon t1 equals 4. So t2 equals 4 times of t. So this is all about third unit. So now we have calculated time domain specifications, time domain parameters, that is rise time, peak time, settling time, overshoot. We can calculate by using expressions. You can also calculate expressions for output by using general expression. So procedure is very simple. First we have to write closed loop transfer function for given system. Then we have to compare this from a standard form and find omega n and theta. Then from these two basic quantities we can calculate all other parameters. Okay, this is all about time domain specifications. Thank you.